Hello, everyone, and thank you so much for joining us today. I'm your host, Adam Lieberman. I'm a distinguished engineer and the head of artificial intelligence and machine learning at Finastra. We're welcoming you for this live meetup, one in a series, part of our Hack to the Future Global FinTech Hackathon. Hack to the Future is a FinTech movement igniting a world of financial sustainability, inclusion, and empowerment. Building on the successes of our previous hackathons to redefine finance for good and build an unbiased FinTech future, we continue to use our position in the market to inspire the FinTech space to be open by default for everyone. This year, we aim to drive engagement beyond our global FinTech ecosystem with 3 key themes that are inclusive and open to all, which are ESG, embedded finance, and decentralized finance. Today, we'll be talking about bias and fairness. When it comes to machine learning, we need to ensure that we're prioritizing people in addition to performance. In this series, we will take you on a journey to understand what bias is and how it can slide into the machine learning pipeline. We have a really exciting session planned, and I'm super excited to have Don Lee join me today. Don, can you please introduce yourself?
Hey everyone, my name is Don Lee. I am a data scientist here in the Innovation Lab at Finastra. I became interested in the topic of fairness because that is really important in the finance industry. I'm excited to be here today to share with you guys what I have been experimenting with in terms of fairness in machine learning models.
Awesome. Thank you so much, Don. So let's jump right in. Don, I just want to check that you can see my screen.
Yeah, I do.
Awesome. Yeah. So hello, everybody. Once again, my name is Adam Lieberman. I'm the head of AI and machine learning at Finastra. And today I'm here with Don Lee, who's a great data scientist on our innovation team. And we're really excited to dig into a primer on algorithmic fairness, which is a big topic that has never been more important. So let's jump right in. Our agenda today will consist of 8 different sections. We'll start with the typical machine learning focus and identify areas where algorithmic fairness should come into play. We'll narrow into fairness and define it to better understand what exactly it is. We'll discuss why it's important from an algorithmic perspective, and then identify ways that bias can slide into our data and models, as well as how we can mitigate them. Next, we'll discuss a few ways which we can measure fairness, and we'll understand some trade-offs between performance and fairness. We'll then end with some resources to help you further explore the field of algorithmic fairness. And then Don's going to take us through a really cool demo of mitigating bias from a trained machine learning model. So let's get started. Every day we are collecting more and more data in structured and unstructured formats, and we're pumping databases with billions of records. Data really is the lifeblood of artificial intelligence, and it's really kind of the fuel to the AI rocket that's taking us on this journey of transforming, so many industries. It's allowing us to automate and create more accurate decisioning, to really increase processing efficiency, reduce, internal operational costs, create better and more personal experiences for our customers and clients, and really analyze trends and patterns in real time. It's super powerful and really proving to change, majority of the industries and domains. We've been solving some really amazing problems with machine learning. For example, we can leverage OCR and NLP to parse documents, required in the lending process and extract information to pre-populate, front-end point-of-sale systems. We're using machine learning to help automate the mortgage decisioning process. We have access to billions of data points to better understand our customer base and create, smarter marketing campaigns. We're challenging traditional FICO scores by using machine learning to better assess the credit invisible, which are individuals with thin or little to no credit. So, to sum it up, machine learning really is playing a role in transforming, not just finance, but the world as a whole. Now, as data scientists and machine learning engineers, we have this very specific pipeline that we all know and love. Data really is the heart of modeling, so we start by exploring our data sets. identify the relationships between them, discover what we have and what we don't in order to solve the problems and the tasks at hand. After we go through this exploratory data analysis, we then need to turn the data into a usable form. We spend time wrangling, cleaning, and pre-processing our data. We then go through an intense feature generation step, and we create these useful descriptions of our data for the problem at hand and for our models to learn from. We'll experiment with different models, tune parameters and hyperparameters, validate our models, and repeat this cycle until we've met our desired performance metrics for this problem at hand. We then focus on deploying and productizing our models, as well as maintaining them and ensuring that they are running in an adaptable form in our production environments. However, there's one thing I think a lot of us really don't think about, and that's to ensure we meet, fairness in our machine learning pipeline. We need to make sure that decisions of our models are fair for the populations that we're modeling, and they're not discriminating, one particular group or, a set of individuals. Algorithmic fairness really, really is an important topic that we really need to embed in this pipeline that we all know and love. And with such a big focus on the ML pipeline, and building robust and generalizable models, there's one quote I really, really love when it comes to bias and fairness in the algorithms we use. And it says, algorithms don't remember incidents of unfair bias, but our customers do. If our models are making decisions that impact people and affect their lives and well-being, it really is imperative that our models are fair and equitable. As data scientists and machine learning engineers, we really need to incorporate the concept of bias and fairness from an algorithmic perspective into our workflow and really keep this at the forefront of our minds. So, what exactly is fairness? Now, fairness is a complex and it's really a multifaceted concept that depends heavily on context and culture. Every problem is unique and has unique sets of data. A use case around AI for credit scoring is much different than a use case around customer segmentation for marketing efforts. Thus, there's not really one true definition for algorithmic fairness. In fact, there are many different ways to define fairness that really can stem from statistical and mathematical definitions or legal definitions for the problem at hand. A great way to define fairness for your problem is to find the legal support and check if there's any definitions that can be used to formulate fairness in a more quantitative manner. Depending on how we want to look at the problem and measure fairness, we need to find the appropriate measure to satisfy. For example, if we're working with HMDA data, which is the Home Mortgage Disclosure Act dataset, and attempting to maybe predict loan status, we can check with the Consumer Financial Protection Bureau for ways to define, a fairness metric. Different definitions of fairness can produce entirely different outcomes. So you might say, Adam, that's not so helpful that there's not, one definition for algorithmic fairness. Kind of give me something, give me some kind of definition. Okay, so here is an attempted definition that I like. In machine learning, an algorithm is said to be fair or to have fairness if its results are independent of given variables, especially those considered sensitive, such as the traits of individuals, which should not correlate with the outcome. To sum this up, we would say something like, an algorithm has fairness if it does not produce unfair actions or representations for our individuals or our groups. And speaking of individuals and groups, there's many definitions that focus on individual fairness or group fairness. Individual fairness focuses on ensuring that statistical measures of outcomes are equal for similar individuals. Or more simply, similar individuals are treated similarly. If you and I are very similar and we apply for a loan, then we should get a similar outcome. Group fairness partitions the population into predefined groups by sensitive or protected attributes, for example, race, ethnicity, gender, and seeks to ensure that statistical measures of these outcomes are equal across groups. So in more simple terms, model prediction should be equitable across the different groups. For example, if we're looking at groups divided by gender, then similar decisions should be made for the groups as a whole. One gender should not be favored over the other. Now, there's also two worldviews with some associated acronyms. The we're all equal and what you see is what you get. The we're all equal worldview states that groups have the same abilities. So any, potential structural biases being different should not be mistaken for a difference in ability. The what you see is what you get worldview states that the observations reflect, these abilities of the groups. I think an easy to understand example is looking at, a FICO score. The we're all equal worldview states that the overall FICO score being different across different groups of people should not be mistaken for a difference in ability to pay off a mortgage. And the what you see is what you get worldview would state more so that, FICO scores correlate fairly well to compare applicants' ability to pay off that mortgage. Now that we understand fairness a little bit and we've conceptualized it, let's try and understand, why it's really important. Here we see 4 cases where algorithms have been used to make a decision and have exhibited unfairness to groups and individuals. We have seen issues with insurance companies using machine learning for insurance premiums that, discriminated against the elderly. We have seen females receive lower credit lines than their male counterparts. We've seen online pricing discrimination and even product personalization steering minorities to higher rates. A quick Google search against algorithms and bias will pull up hundreds of examples where, the models just unfortunately were not tested for fairness before they were released into the wild. And really the point of this is that, bias is prevalent all around us. And, our customers are aware. When customer trust is lost, there's no guarantee that we can get it back. Here's a few quotes from individuals who have experienced, algorithmic bias firsthand. It's totally unfair because not every woman is the same. They've already labeled me as a low-income person. The bank said I can't afford a $950 mortgage, so I'm going to pay $1,400 in rent instead. Our customers are aware algorithmic unfairness occurs. And, if we were to put out lending models that affect the lives of our clients and customers, we've got to be sure that they're tested for fairness. And, even more, there's feedback loops. The decisions made by unfair algorithms can be propagated as, a next round of training data, which our models, again, learn from and evolve from. This feedback loop can really cause a vicious cycle that just propagates biased data. So we need to be very, very careful about biased models and potential feedback loops to prevent, the reinforcement of this bias. So for some motivation around this, I took some publicly available HMDA data and a very popular adult income data set, and I built some preliminary machine learning models. I left, all the sensitive attributes out. I made sure I had balanced data, created some nice features, and I got some pretty high performing models. And if I didn't know anything about fairness, I would say, hey, this is awesome. These are really great models. However, I did some inspection into fairness, and looking at the HMDA data on the left, I examined race. We can see the probability of a loan being accepted given race on this chart. Look at the difference between the orange and blue area. Here we can clearly see that the probability a loan is accepted given the race is white has a much higher prediction distribution than not white. If this was fair, we should see the lines having very, very little overlap. Similarly, with the adult income data set on the right, we can see that the females had a much higher probability to have a predicted income of less than $50,000 compared to males. Simply looking at performance can be super dangerous, even if we leave out sensitive attributes like race, ethnicity, and gender. So what can cause bias to model unfairness? There's 3 core areas where bias can kind of creep in. Bias in our data is what our data contains. Bias in algorithmic design is how the model is designed, and bias in human use is how we as humans actually use the model results. In the next couple minutes, we're going to dig into each of these categories and understand how bias actually comes into play. But first, we need to note something, and that is bias in, bias out. In machine learning, you might be familiar with the GIGO principle, which stands for garbage in, garbage out. If we put bad data into a machine learning model, we're probably going to get a junk or a bad machine learning model. And the same is true for biased data. If we put biased data into a model, we should expect biased results, right? The machine learning models will be essentially learning to replicate these biases that are found in the data. So let's now talk about the category bias in data. One thing that we have to accept is that data can be inherently biased with and without intention. Humans have knowingly and unknowingly made biased decisions, which have become data points, available to train a model. Often, data scientists, we're working with data sets spanning decades, and to achieve scale, it's really almost impossible to manually inspect every single data point with a domain expert. For example, the embedding model that we leverage for NLP tasks were trained on massive sets of data that were scraped from the internet. And, as we know, the internet is not a bias-free place, as humans have contributed to many biased articles and information. However, to achieve scale and get enough data to train models, researchers have had to resort to some of these methods. But just because we leave out sensitive data from our models, does not mean that models do not have links to sensitive fields. Related fields can serve as what we call these proxies and be links to sensitive data. For example, we know gender, ethnicity, and religion are really not to be used in any kind of lending model designed to predict, mortgage approval. However, if we use postal code or name in the model, we could potentially derive things like ethnicity from the model or gender from the name. These can serve as, these hidden sensitive links to the data we originally left out. So when constructing features, we might think we're removing the sensitive fields. However, there can still be links to them, and this is where bias can slide in. Now, measurement bias. Measurement bias is all about how our data is measured, collected, and stored. Faulty equipment, differing systems, collecting data, and regional differences can cause, really, really similar data to actually look different. For example, we have the same apple on the scales on the left. One scale says the apple weighs, 4.1 ounces, and the other scale says the apple weighs 4.3 ounces. And, this is due to some faulty equipment on our scales, and it's caused, the data behind the apple to look different. And this may not sound like it's super important, but it's contributing to different labels that could be used. And this is, in a sense of bias. Sometimes we look at a data set and, we decide to just delete some unimportant information, or so we think. Often during pre-processing, when we're deleting outliers, removing nulls, et cetera, this is where we can actually introduce bias. And to illustrate this, below we see that looking at this chart, we have Wyoming data and Florida data, and 98% of our data is Florida, and we've got 2% that's Wyoming. And just looking at this, we say, hey, there's barely any Wyoming data. Let's just toss it out. So we remove it because there's really nothing there. However, if we do so, we might fail to capture that people in Wyoming are spending double that in Florida. So we really need to be careful about the data that we're moving, because our models may fail to capture this really important information, which in a sense, is another form of bias. Now, sample bias. This is very, very important. Sample bias is all about how we choose our training samples for our model. We need to ensure that the training population matches that of the population we're actually wishing to model, which is our target population. If not, our model's not going to have experience or exposure to a diverse set of data points that make up this target population. For example, on the left, our target population consists of these pink, these blue, green, and gray dots. But if our training samples only consist of blue and purple circles, we're not going to have any exposure or learning for the pink, green, and gray. So when these data points come into play for getting predictions, our model's not going to know how to predict against them. And here, the sample selection is just not representative of our target population, and we're introducing some bias into our model. So label bias. In machine learning, supervised learning, we often work with labeled data. Often humans label data, but we also see, some programmatic and system-based approaches. But if similar data points are labeled inconsistently, we introduce a bias through the labels that we're actually trying to learn. For example, here we have, some environmental, social, and governance labels, and 3 environmental text statements that we want to label and classify. We see that statement 1 and statement 3 are very, very similar, but statement 3 has been labeled incorrectly. So this is an example illustrating label bias. And finally, we get into emergent bias. The future, as we know, is unknown. And bias, which emerges some period after an algorithm is created and used, is called emergent bias. And this can be from, new thinking and ideology. It could be from changing societal knowledge. It could be new trends, new laws, new technology. It could be population shifts, and really an uncountable number of ways. When beliefs and ideologies change, our models can become outdated, and it's very, very important to keep these models fresh so that we can monitor this, data drift. It's very, very difficult to anticipate emergent bias, so we do need to keep a very close watch on our data for this. And how do we mitigate data bias? To mitigate bias in data, we first need to start with the business problem and select the data that's appropriate for modeling. Here we really want to work with domain experts and our legal and governance teams. We need to make sure that our data is representative of our target population. And if it's not, we need to somehow find a way to collect more data and get this representative data set. We need to make sure, like we saw, that our labels are consistent and that, our samples are weighted appropriately, and, potentially explore models like, synthetic data models, if they're not. So there's many, many more steps, but these are kind of four core ones to keep in mind. So let's now move into bias behind algorithmic design. Now, data is not the only thing that can lead us on a path to unfairness. When we have a machine learning model related task, we obviously want to maximize the performance and minimize errors, right? We want a model that has great performance, not a model that has poor performance. However, when we focus purely on performance and the objectives of algorithms, we can introduce a bias from our learning objective by benefiting, potentially a majority group over a minority group. We really do need to define appropriate fairness measures in terms of data and algorithmic objectives to ensure that, all groups are bias-free. Instead of looking at purely, performance-related metrics like accuracy or F1 score, we can optimize for particular fairness metrics, which we're going to peek at into the next section. Now, depending on the model, we often learn weights from our features, meaning one feature can be more important for a model's decision than another feature. For example, let's say we have, an insurance premium model that takes into account 2 features, credit score and driving record. The model is trained, and credit score ends up becoming 3 times more important than driving record. Since credit score is weighed, 3 times more heavily than driving record for the model's decisions, we might see an unfair advantage for bad drivers who have great credit scores compared to excellent drivers who have, just pretty good credit scores. So weighting bias can definitely occur. So it's really important to, inspect the interpretability around our features, as, these could lead to a potential bias. So to mitigate bias in algorithmic design, there's 2 main categories. There's in-processing and post-processing. In-processing modifies the algorithms directly by incorporating fairness into that objective function, or adding constraints and regularization to the training. Basically, within processing, use fairness metrics, which we're going to take a look at next. For post-processing, we're adjusting the outputs from the model so that the results are, more fair. Basically here, leave the model, don't touch it, and just adjust the outcomes from the model. So let's now get into humans. There's a thing called confirmation bias. And in terms of machine learning, it's the tendency to choose results from the model that align with, our human current beliefs or hypotheses. Basically, you have some preconceived notion and you view the model result, which skews, your belief. Humans, we do have a responsibility to use model results correctly and in a bias-free manner. So, bias can stem from the way humans are actually using these models and the results from the models. So to mitigate bias in human use, it's tough, right? You have to educate your end users around the algorithm and really just set, kind of limitations and, be very, very clear with the model's intended purpose and how it should be used. You really want to guide your users on, the model's point of view and, what the output actually means. So now that we know that bias can leak into our data and spoil our models, let's take a look at a few fairness metrics kind of at a more high level. Like there are many definitions of fairness, there are many, 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 many metrics of fairness that we have at our disposal. Here's a list of just a few metrics. There's some pretty generic metrics, some that are specific to group fairness, others that are a little more specific to individual fairness. And sometimes we just got to craft our own for the use cases. And really, sometimes there's cases where we can use some of these out of the box calculations. We don't have time to go over each of these, in depth, but Dawn's going to touch on a few of them in her demo. This is just a nice list that you can refer to for some of the more popular metrics like disparate impact, equalized odds, and so forth. Now, I know looking at that list, it could be, pretty overwhelming, especially when you're first, just diving into this field of fairness. The University of Chicago has actually created a fairness tree that you can kind of, trickle down to find out which fairness metrics you should look at. This is by no means a hard and fast rule book, but it is a great place to start, to understand fairness for your problem at hand. We've got to remember that there's not just one definition for algorithmic fairness, as it's highly, highly dependent on the, the problem at hand and, the data that we're working with. So determining, the right measure to use must, take into account the proper legal, ethical, and even the social context. So now that we understand a little bit, how we can measure fairness, we need to talk about some of the trade-offs. It would be really, really nice if we could have our cake and eat it too. When we start discussing fairness, there is, this inherent trade-off with accuracy. As we seek to optimize for fairness and increase it, there's a chance that we compromise, our model's accuracy or performance. There's a lot of, scientific papers that you could refer to that support this. We have to understand that, the aspiration of a fairness-aware algorithm is to achieve a model that allows for higher fairness without, significantly compromising that accuracy or performance, or other alternative notions of utility. However, there is a potential to see a drop in accuracy with an increase in fairness. And really, looking at this pyramid, it's kind of like a balancing act. Now, when we look at the predictive nature of our model versus, the bias exhibits, we can measure it in 4 quadrants. On the y-axis here, we have the predictive nature of our model. And on the x-axis, we have, the amount of bias. If we can get a model that is more predictive and has less bias, that's a complete win-win. That's what we always want. However, sometimes with less bias, we do get a less predictive model, like we mentioned on the previous slide. Here we have a trade-off, a more fair model for a less predictive model. If we look at the quadrant in the bottom left, this is the absolute worst case scenario. We get a less predictive model with more bias. And this is clearly the area to avoid. At the top left, we have a more predictive model with more bias, which can be, risky by putting an unfair model out into the wild. But, based on our use cases, we've got to decide our risk levels and really this battle between predictive nature and bias. But, if we can get to that top right corner, that is the sweet spot. So we just went through a lot very, very quickly, but let's take a look at some resources that you can continue to look at, as you explore, this big, big field of fairness. If you want to dig into technicals, I would definitely check out this book called the Fair ML book. There's also a linked paper below by Pesach and Shmuel, which is a great, great survey to this field of fairness. Additionally, we've listed a bunch of really great blogs and a few GitHub packages and libraries by Microsoft and IBM that will help you get started. Together we can build the future. Algorithmic fairness is really a huge area with many different areas to explore. What we're now going to do is jump into a demo with Dawn as she shows us the process of actually taking a machine learning model that was trained and debiasing it with one of the libraries called Fairlearn, which we had in our previous slide. So I'm going to stop sharing, and Dawn, I'm going to pass it over to you.
Sounds good. Can you see my screen?
It is pulling up. We got you.
Okay. Today we'll demonstrate how to use the Fairlearn package developed by Microsoft to assess and mitigate issues with fairness in machine learning, specifically a classification problem using the census data. So census data is a public data set and it's available through scikit-learn's dataset package. And this data set contains attributes of 32,000 individuals, where some of these attributes are really sensitive. The original problem was to predict if each individual in the data set had an income above or below $50,000. But for our purpose today, we'll treat the label as a representation of the individual repaying a loan in the past or not, and a decision will be made as whether to offer this individual a loan or not based on the predictions of our model. So the model will be first trained without giving it any awareness of fairness. We will evaluate how much unfairness exists in the model's predictions with different fairness metrics. We will also demonstrate how to mitigate unfairness in the model by utilizing threshold optimizer and grid search provided by Fairlearn. So first, let's get started by importing all the necessary modules and packages, and then load the data using scikit-learn dataset. Then we will pre-process the data. So here's a glimpse of the data itself. There are many, many features, and this is the target variable, which is already converted into 0 or 1. And then we will select the gender of an individual as the sensitive feature, and then we will convert this feature into 0 and 1 as well, where 0 represents a female and then 1 represents a male. The sensitive feature itself will be extracted out of the data set, and we will do standard pre-processing here on the rest of data so that it can be used for our machine learning model later on. Next, we split our data into training and testing sets so that we can train our model on the training set and evaluate the model performance on the testing set. Notice that we also need to create training and testing sets for the sensitive feature itself because we need that later on. Okay, here's just some tidying up, very indexing these sets. Okay, next, we train the machine learning model without any fairness awareness. For our classification task, we will implement a light GBM classifier. We will train it like how we normally would, fit the model to the training data, and then evaluate its performance with the testing data set. Here is Fairlearn's dashboard. It's a very great functionality for visualizing the testing results. So let's get started. Here we've selected gender as the sensitive feature. And for our performance metric, we can select balanced accuracy. And then there's two parts in this dashboard, disparity in performance and then disparity in predictions. In terms of the performance, the dashboard shows that males actually have an over-prediction about 3 times greater than females. And then for predictions, the disparity in selection rate is very concerning. It's basically saying that males are offered loans at more than 3 times the rate of females. Remember that we already dropped the sensitive feature gender from our training data, but the model still favored males over females in the loan decision. Since there are usually other features correlated with the sensitive feature itself, like Adam mentioned, the proxies, then that will eventually lead to disparity in the results. And to make our model more fair, we need to let it be aware that there's actually an issue of unfairness. This can be done through Fairlearn's post-processing and reductions packages. So here's the fun part that we can mitigate a model's unfairness with threshold optimizer and gray search. So the model's output will be adjusted to fulfill the parity constraints that we specify. Threshold optimizer is a classifier obtained by applying group-specific thresholds to the provided estimator. And the thresholds are chosen to optimize the provided performance goal, subject to the provided fairness constraints we have. In our case, we'll subject it to a fairness constraint called demographic parity. And demographic parity requires that individuals are offered the opportunity independent of their membership in the sensitive class. So in our case, that means females and males should be offered loans at the same rate. Here we specify an optimizer where the estimator is our original model and is unaware of the fairness issue. And then we put the constraint as demographic parity. So in the fit method, we specify which sensitive feature we want the model to be aware of. And then in the predict method, it will predict label for each sample in the X test while taking into account sensitive features. Then we list a bunch of very important fairness metrics and then create some helper functions for calculating fairness metrics that we can use to compare our models. And then we can compare our new model after using threshold optimizer versus the unmitigated model. And then you can see there are quite a few metrics to refer to, but here we will focus on demographic parity difference. And this is just a different phrase for demographic disparity. We would like this number to be as low as possible. And then we can see that the threshold optimizer actually did an amazing job with reducing this number. And of course, we also care about accuracy for the whole model. And looking at the overall AUC, we see that we did lose some accuracy with threshold optimizer, but both the false positive rate difference and the false negative rate difference dropped very significantly. So that's actually a win for the threshold optimizer. Next, we train gray search, which is another method for mitigating bias. And the gray search class requires a standard machine learning estimator as well, so we can put our model in. And then gray search works by generating a sequence of relabelings and reweightings and trains a predictor for each set of these relabelings and reweightings. The gray search algorithm has a standard fit and predict methods as well. And the fit method also require that we put the sensitive features in. And then here we calculate some metrics such as demographic disparity, balanced accuracy, and AUC score. And then because we have so many combinations of relabelings and reweightings, we want to find the ones with, we want to find the models that we trained with Gray Search that has really low values of demographic parity difference and high accuracy, because those are the metrics that we care about right now. So here we filter out the model, and then next we can compare the filtered out Gray Search models with unmitigated and also the threshold optimizer models. And here's the results for the metrics. And ideally, we would like to have a predictor that has high accuracy and low demographic parity difference. So that's with respect to the sensitive feature gender. But there's also, a trade-off, like Adam mentioned. Here we were able to decrease the demographic parity difference with threshold optimizer and Gray Search. Threshold optimizer provides a better fairness result in terms of the demographic parity difference, but it did lose some accuracy in the overall ACU. However, if the requirement for low demographic disparity is not super strict, then one of these Gray Search models will suit the need, as they have a slightly higher demographic parity difference, but also higher accuracy than the threshold optimizer one. So really, depending on what the business case is and what you're looking for or what you value the most, you can find an optimal trade-off by comparing these results. And that is how you can mitigate unfairness in the machine learning model using Fairlearn. And I will be posting the repository to our code base on our Discord, so please check in there for the code. And if there's any questions, please feel free to post in the chat or message me our Discord page. Thank you.
Awesome, Don. Thank you so much. That was very, very informative for us, guys. Like Don said, if you're looking for the code base, join our Discord, come chat with us, and we will have the code available. I see a bunch of questions and comments, so let's jump into those. Clement, first of all, we're very excited to have you. Thank you so much for joining. Tim, so the first question that we see, it says, just how cool is it to be known as a data scientist in this age of transformation? I'm a data scientist, Don's a data scientist, so we think it's pretty cool. But on a serious note, there's a lot of power within data, and having the tools, the understanding, and the frameworks to actually build off data is very, very valuable. So I think it's pretty cool. The second question we're seeing is, why don't algorithms remember? Shouldn't that be a part of a machine learning feedback loop? And this is a big question. It's actually a great question. Depending on the kind of model, there is some kind of memory associated with it. We also need to remember that data drifts. So if we've trained our model, on one portion of data and the data starts to look different and it's not, continuously trained, we're going to see a degradation in that model. So we really do need to look out for data drift. But also, machine learning feedbacks are very important. Sometimes we want to have a human in the loop, but also, if we can get that feedback, from our predictions, if we're getting them wrong or right, we can continuously keep a fresher model. A question from Clement. I would like to go deep into data structures and algorithms. Do you have any space where I can fit in? Clement, definitely join our Discord, and join our hackathon. We have a lot of really interesting things going on, and we would love to chat with you. The next question I'm seeing is, what is a FICO score? So a FICO score is a 3-digit number that is based on the information that's in your credit reports. And it really helps lenders determine, how likely you are to repay a loan. Our next question I'm seeing is the mortgage versus rent not being a good example. It demonstrates a lack of understanding of the total cost of ownership versus the fixed cost of renting. And Tim, that's a good point. And this was actually not an example that we were showing, but it was a direct quote from a customer. And this really highlights to show that, customers are trying to understand algorithmic fairness and bias. They may not get it completely right, but this was a direct quote from a customer that we had found from another party. So yeah, customers are, aware. Customers want to be treated fairly, and you can go back and take a look at those slides. Those are all different customers showing how they feel and what they think is fair or not. And this is why we believe it's very, very important for end users, customers, and everybody to really understand what algorithmic bias and fairness is. The next and last question I'm seeing is, do we risk reverse bias when humans are deciding what bias needs to be remedied? And that's a really good question, because it really depends on the human. We had touched on that, there are humans that are, incorporating bias intentionally or unintentionally into data. So if, humans are involved in the loop and, they are acting in a biased manner, then, we're risking putting more bias in. But, at the same time, if humans are responsible and making their best effort to reduce bias, we can actually mitigate, bias from data. And this is really what we want to seek. I'm now seeing one more question. This is actually an amazing question. How can blockchain technology help mitigate algorithmic bias? And, to answer this, if we look at machine learning, oftentimes, we're really seeking to get, that diverse set of data, that data that really represents, our target population. But, it can be really hard. Maybe I'm in the Southeast and I don't have access to data in the Northwest or the West Coast. And I really want to build, this one overall more generalizable model. And, I just don't have that training data. There's actually some newer research about leveraging blockchains to collaboratively train machine learning models. So, if Don's in one region and I'm in one region, and we have some other friends that are in different regions, and, we all have, different data for the same problem, we can collaboratively train a model together and leverage the blockchain for it. So it's definitely newer research, but if you do join our Discord, we can ping you a link to that research paper. And those are all the questions that I am seeing. Thank you all so much for being here. We're really excited to have you. Bias and fairness is a very, very important topic. We got some amazing questions. We're excited to have everybody join our hackathon. And if you join our Discord, and you have any other questions, feel free. We'd be excited to chat with you around it. So thank you, Don, so much for being here. And thank you all.